Don't forget to subscribe and ring that bell.
Howdy, neighbor. Welcome back to the 2018 AP Calculus AB exam practice exam that College Board gave to us. And we are going to finish this exam. It's been a wonderful, wonderful exam. And this video is for the very last problem of Section 2, Part B. Free response question 6. We don't get a calculator. No. But don't worry, because we are smart. And the algebra that they give us in these problems without a calculator is typically a lot more doable than when we get a calculator. Okay? So, without wasting any more time, let's finish this bad boy off. Number 6 reads, consider the curve given by the equation 2 times x minus y equals 3 plus cosine of y for all points on the curve where the derivative is in the interval from 2/3 to 2 inclusive. That's not an interval on the x-axis or for an x value. That is an interval for the derivative. All right? 6a asks us to show that the derivative dy dx is 2 over 2 minus sine of y. All right, let's begin this bad boy. All right. Well, I'm looking at what they gave us here. And right off the bat, I'm saying that I cannot get y's alone. I've got to take this derivative implicitly. That means that I will take the derivatives of my x terms like normal. But anytime I take the derivative of a y term, I do it just like it's an x term, except I need to write dy dx right next to it. So let's begin. The derivative of 2, well, that's a constant out front, so we're just going to keep that. Now I take the derivative of x, which is 1, minus, all right, the derivative of y, which is 1. But when I take the derivative of y, I put 1 dy dx, okay, equals. The derivative of 3 is just 0, so I'm not going to write that down. The derivative of cosine is negative sine of y times the derivative of the inside, the chain rule. Okay, the derivative of y is 1, but dy dx, because we're taking the derivative of a y term. All right, so now we just got to clean this up. And I think the first thing we do is let's distribute this 2 in here. 2 times 1 is 2, minus 2 dy dx's. Okay, equals. We still have the right side, which has not changed. It's the sine of y dy dx. All right. So what I want to do is, if I look what they ask of me here, they want me to get dy dx alone. So I've got to get the terms of dy dx on the same side and then factor out the dy dx. So, yeah. Let's add 2 dy dx to both sides. Plus 2 dy dx, okay? And when I add this 2 just drops. It comes along for the ride. Whee! And I have 2 dy dx minus sine of y dy dx. Okay? Now, look, this is beautiful. These are both on the same side. It's good. So what I'm going to do is I'm gonna factor this out like it's a GCF. Okay? So let's continue that right now. This 2 still comes for the ride. Whee! It's there. I love the wee noise. Dy dx gets factored out. Times what's left? 2 minus the sine of y. Now, the only thing remaining to get this dy dx alone, okay, is I'm going to divide both sides by 2 minus the sine of y. This goes bye-bye. What I do to one side, I have to do to the other. Okay, and that's it. dy dx is 2 over 2 minus the sine of y. What do they ask for? 2 over 2 minus the sine of y. We've done it. Perfect. I love when they give us the answer. We just got to get there. I love it. 6b. For negative pi over 2 to positive pi over 2, a y value is in that interval. So my y has to be between, if you want to convert this radians to degrees, it's really from negative 90 to 90, okay, which is negative pi over 2 to pi over 2. My y value has to be in that interval. It does not include, it's not inclusive. It just has to be in between those two values. There is a point P on the curve through which the line tangent to the curve has a slope of 1. This is big. Okay? Find the coordinates of that point. All right. So here we go. First of all, if the slope is equal to 1, my God, fireworks should be going off in your brain. That means the derivative, which is dy dx, has to equal 1 because slope is the same thing as derivative. All right? And in part A, if we could not figure out algebraically how to make the derivative equal to what they gave us, and we mess that part up, they still give us the derivative. So we could still do part B, even if we were to mess up our algebra from part A. But you know what? We didn't mess it up because we're good, we're smart, and we know what we're doing. So my derivative has to equal 1. So right off the bat, I'm going to make that known. Okay, my derivative, which is 2 over 2 minus the sine of y, has to equal 1. Okay, now I'm no math genius here, but I know that my numerator here will never change. It will always be 2. Okay, 2 over what gives me 1? Well, 2 over 2 is the only way I can get my fraction to be 1. That means this denominator right here has to be 2. Okay? This numerator has to be, this denominator has to be 2. So this denominator has to be 2. So let's say 2 minus the sine of y, okay, has to equal 2. If this expression equals 2, if that equation is true, that means my derivative is 1. Okay, this has to be a 2 on the bottom. All right, so let's take a look at what I've got written here. What's the only way that my equation works? If the sine of y is equal to 0. Because 2 minus 0 is 2. Okay, so sine of y has to be 0. Sine of y has to be 0. And let's remember, y has to be between negative 90 and positive 90. There's only one value of y that makes that happen. Okay, and I'm going to refer to the graph, although you can probably refer to the unit circle if you want. I just like the visual of the graph. Here's 0 degrees. Here's 90 degrees. Here's negative 90. Okay, sine is the S. Starts here, goes up, comes down, goes up. But I don't care. And then it continues this way. I don't care about all this or after positive 90 because the interval they give me is between negative 90 and positive 90. It has a value of 0 at one point right here at 0 degrees. So y has to be 0 because the sine of 0 would give me 0. Okay, that was my logic as far as solving for the y value to get my slope of 1, which they gave me initially right here. The derivative had to be 1. Okay, so let's just go over this quick. That means my derivative is 1. My fraction that they gave me for my derivative has to be 1, which means that's 2 over 2. So I take my equation, set it equal to 2, and realize, oh, look at me. sine of y has to equal 0. And the only value for y that I can plug in to get a 0 is when y is actually 0. Whew, that's a lot. You know what the sad part is? That's only one of the two values I need for my coordinate. I just got the y value. Now I need the x value. All right? So let me go here, we go here, here. So again, I'm trying to get a coordinate for P. Let's not forget what we're doing. Find the coordinates of P. We just got a y is 0. So now we need an x. Okay? Where do I go if I have one coordinate and I need the other coordinate? Not the derivative. The derivative is a slope. I go to the original equation. The original equation, if I have an x and need a y, or in this case, I have a y and need an x. So the original equation is 2 times x minus y equals 3 plus the cosine of y. Now let's keep in mind our y is 0. So we're going to replace this y with a 0, replace this y with a 0. And we're solving for x. So 2 times x gives me 2x equals 3 plus the cosine of 0. Let's use our little graph up here. We're going to do it in green. Cosine's the cup. Starts up here, comes down, and makes a cup. At 0 degrees, the cosine is 1. The cosine of 0 is 1. You guys are going to have to know your trigonometry values. Okay? So 2x equals 4. If I divide both sides by 2, x equals 2. There we go. This is my golden answer right here. Did a lot of work and a lot of explaining, but I want to make sure you understand it. Okay, so find the coordinates of P. It's on a curve where the tangent line has a slope of 1 in between negative 90 and 90. It's the point 2, 0. Done. 6C. Determine the concavity of the curve at points for which y is in between negative pi over 2 and pi over 2. Or in terms of degrees, negative 90 and 90. Give a reason for your answer. All right. Give a reason means we need to explain. Okay? So let's start. And again, bells and whistles go off. Concavity is a second derivative with respect to x. Okay? It's a second derivative with respect to x. And I think, you know what? Isn't it supposed to it's a second derivative of y with respect to x? Either way, I think the 2's go that way. I think I mixed them up. Either way, let's get going. So we need to look at our first derivative. Our first derivative was 2 over 2 minus the sine of y. You know what's great? For 6c, this is the first derivative. We need to get the second derivative, okay? I'm finding the second derivative. This is what I'm finding, but we got to remember that this is the first derivative, okay? I don't want to confuse you there. This is what I'm finding. But what's great about this is 6c, we need to use the first derivative. For 6b, we needed to use the first derivative. So 6a, that's why they don't have you figure it out on your own. That's why they give it to you and say prove it. So you should still be able to do 6b and 6c, even if you messed up this algebra. I love that they did that, okay? So, okay, we need to take the derivative of the first derivative. This is definitely a quotient rule, okay? It is low, which is 2 minus the sine of y, d high, the derivative of above, the derivative of 2 is 0. That's nice. That makes everything go bye-bye. Low, d high, minus high, which is 2, times d low. The derivative of 2 is 0. The derivative of negative sine of y is negative cosine of y. Again, implicit differentiation, times dy dx. Okay? I draw a line and I square below. 2 minus the sine of y. This whole thing is squared. All right. Here we go. So now what we need to do. Yeah, Yeah, I said it. Now what we need to do is we need to kind of, we can't have dy dx. Okay, we can't have dy dx in here. Okay, can't have that in there. So we got to substitute that out. So let's start to simplify this. First of all, 0 times anything is 0. This is going to go bye-bye. That's just going to become 0. So it can go bye-bye. So I now have -2, or yeah, -2 times a negative cosine of y, okay, times dy dx. Okay, but we can't leave dy dx in there. So what are we going to put right here for dy dx? Well, we know what dy dx is. Dy dx is 2 over 2 minus the sine of y. Okay, all over the bottom, which is 2 minus the sine of y squared. So in order to know if this is positive or negative, it would be easy for me to kind of evaluate now, but let's make it easy for everyone. I don't like having a fraction in a fraction, especially when I have to evaluate it, okay? I'm not just plugging in a 1 or a 0 or anything like that. Let's multiply the top, okay? Let's multiply the top by 2 minus the sine of y, okay, over 1 if you want. This will cancel with this. What I do to the top, I need to do to the bottom, okay? And let's not forget our basic rules of exponent. This is squared. This is the power of 1. So anytime I multiply common bases, I add the exponents. So the bottom is going to be 2 minus the sine of y cubed. That's the bottom. That is the denominator. The numerator, if you want, we can multiply -2 times +2. Okay, we get -4. All right, and -4 times, we still have negative cosine of y. In fact, a negative times a negative will give us a positive in that numerator. So I end up with 4 cosine of y all over 2 minus the sine of y, or this whole thing is cubed. We just found the second derivative and simplified it so it's nice and compact. Now, the question is, okay, and why we need that is concavity is second derivative. If the second derivative, I'll do it this way, is positive, it's a smiley face or concave up. If the second derivative is negative, it's a sad face or concave down. All right? So we need to determine, is this going to be positive or negative? Now, keep in mind, they give us this here from -90 to +90, or -π/2 in radians to +π/2. So I'm going to reference once again, okay, I'm going to reference once again my graphs, and you could do this on the unit circle. All right, so if I got this, and I got this, and here's 0, here's 90, which is π/2, or 90, and here's -π/2, or -90. Okay, we go up to 1 and down to -1 on the y-axis. Here's 0, y-axis. Sine is the s. Starts up here, curves up here, gets an s, right? It eventually comes down here, does that. But let's get rid of that, those that. And then it continues down here. That's how sine is, okay? And it would continue like the s. But let's get rid of that. Cosine is the cup. Starts up high, and then comes down, and it would continue like a cup. Okay, but we don't want that part. We just want to stop at 90. Okay, and then it would just continue this way, and it would, if I wanted to, continue down a cup, but we're not going to do that part right there. Let's get rid of this. So this right here is my cosine and sine in the interval they're telling me. How come? The interval is right here. Okay, so let's look. First of all, notice that cosine, which is the green one, it's always positive. It's always above the x-axis, right? So it doesn't matter what value I put in for here, the output will always be positive. So I've got 4 times, well, cosine of y will always be positive. So my top will always be positive because a positive 4 times a positive value will give me a positive result or a positive numerator. Now let's look at sine of y. As I'm looking at this, anything on the right side, sine, okay, this is sine. I hate to do this in red, but okay, sine is positive anytime it's above the x-axis. And it's negative anytime it's below the x-axis. So we have an issue, but not really. Okay, when sine is positive, let's worry about the positive, okay? When I have a positive value here, that means I have 2 minus a positive value. Notice the biggest this ever gets is 1, a positive 1. This will never get bigger than a positive 1. Okay? 2 minus 1 is still a positive value. It's a positive 1. And don't forget, I got to cube this whole thing on the bottom, don't I? 1 cubed is a positive number. So my second derivative will be positive altogether. But what about below when it's negative? Okay, let's do this. What about this area? What about when it's negative? Okay, let's make my positive 1 here a negative. Again, it doesn't get any smaller than a negative 1. It doesn't go any deeper than that because it curves back up. So if I subtract a negative 1, subtracting negative is like adding, isn't it? That would give me 3. 3 cubed is still a positive number, positive 9, and we still get a positive value. So my second derivative is always positive, which means determine the concavity is going to be positive. So let's write this, and we got to give a reason for our answer. Okay, this is the second derivative, all right, and we're just going to write the following. Okay, it's concave up. Let's first establish that. How come? Since d to the second derivative of y with respect to x, second derivative is always positive. There you go. You answered a question. That's 6C. This is a weird question. I haven't really ever come across another one like this. So I'm glad we're doing this oddball here, but I wouldn't worry too much about it. Let's go over it, okay? 6D. Let y equal f of x be a function defined implicitly by 2 times x minus y equals 3 plus cosine of y. That is continuous on the closed interval from 2 to 2.1. And differentiable on the open interval from 2 to 2.1, not inclusive, okay? The first interval of continuity was inclusive. The differentiability is not. That's not so important right now. Use the mean value theorem on the interval from 2 to 2.1 inclusive to show that f of 2.1 minus f of 2 is in between the values of 1/15 and 1/5 inclusive. Now, what the heck, man? Do you know what this problem is really asking you? It's really asking you if you know what the mean value theorem is. That's all it is. The only thing that sticks out to me that makes this a typical calculus problem is this right here. Now, I've said before, there's the average value theorem. The average value theorem is with integrals. I do an integration of some function, and I have to multiply it by 1 over the difference of those functions. That's the average value. The mean value theorem is with derivatives, not integrals. That means there's some derivative. There's some value where I can take the derivative at one point that is the same as the derivative of the 2 endpoints of our interval. Okay? That means my change in y over change in x has to equal the derivative at some point. Okay? And in calculus, what we do for this, instead of writing it like this, we write it like f of b minus f of a all over b minus a. So that can be the right side of the mean value theorem. So first of all, this is the interval that they want us to use. Use the mean value theorem, which is this puppy right here. Okay, and I'm going to get rid of this for a second because we're going to use the calculus version for this problem. All right, on this interval. So guess what? Here's my a, here's my b. So f, and they're giving us f of x, right? The derivative of f of x has to equal, okay, it's supposed to be f of b minus f of a all over, I'm leaving space here, b minus a. Well, in this case, we know it's 2.1 minus 2, and up here it's f of 2.1 minus f of 2. Because if I have 2, how do I get the y? I plug it into the equation of f. I have 2.1, how do I get the y for that? I plug it into the equation. Now let's take a look at what they want us to show. They want us to show this here. What should jump out is, you see this right here? That's the numerator. So what I'm going to do right now is I'm going to take this right here, okay, and I'm going to plug it right in the middle here. And I'm going to try and isolate my f of 2.1 minus f of 2. All right? Yeah? 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 We okay? Yeah? All right. So let's go ahead and do that. So I'm going to take f of 2.1 minus f of 2. This is what I'm going to need. Okay, that's still over 2.1 minus 2. But what numbers, like I can't just put 1/5 here, and I can't put 1/15 here. I mean, I want them there eventually, but what do I do here? This drove me crazy until I figured it out. Let's go back to 6a. When we read this, and notice I circled this a million times right here. Read it. I did all this work to get this right here. Then for 6b, I still needed this. Yeah, I'm still circling it. And then for 6c, I still needed this. Look at this right here. We just thought that this was just something that they just threw in at the end. The derivative has to be bigger than 2/3 or equal to 2/3 and less than or equal to 2. That is given to us for a reason. This is my derivative. Okay, my derivative should be this thing right here. This is my derivative, which means it should be greater than or equal to 2/3 and less than 2. That's what they gave us right from the beginning. We're finally using it. I didn't even realize we were going to have to use it. Okay? Now let's just simplify this so that, you know, I can get my numerator alone. Because remember, I just want the numerator here. Okay, that's the top of this. Let's get rid of the bottom. The bottom, if I subtract them, I get 0.1. Okay, so I'm going to multiply the middle here by 0.1. So these cancel. But what I do to the middle, I also got to do to the outside. Multiply that times 0.1. And multiply this by 0.1. All right, so let's clean this up just a little bit. I got 0.2 over 3 is less than or equal to my f of 2.1 minus f of 2, which is less than or equal to 0.2. It still doesn't look like this fraction of 1/15 and 1/5 yet. Okay, but notice they don't like decimals and fractions. Well, first of all, this here, let's change colors. Let's go purple. Yeah, orange. This here, purple. Definitely purple because orange is too much like red. 0.2 is the same as 2 over 10, which is 1/5. That one's done. Okay, but this here, we know 0.2 is 1/5, right? So let's put 1/5 over 3. We just figured out that 0.2 is 1/5. Now, let's multiply the top by 5, so we get rid of the fraction. What I do to the top, I also have to do to the bottom, don't I? 1 over 15. Boom! Oh my goodness, we are done. That was strange. I have not seen a problem like this. I mean, every once in a while we get an outlier that I've never seen in another test yet. And there it is. So in summary, you have to know that we got to use that mean value theorem, okay? Here's where I highlight the heck out of everything. No crayon. You need to use the mean value theorem, which is that the derivative is equal to the average change in rate, the slope between 2 points. So we figure that out right here. I use that piece of information they give me and say that my derivative is between the interval they give me, and all I got to do is simplify it and get rid of the decimals. It really is that easy. It's crazy. Crazy. Don't freak out over this because I doubt you'll see one like this. You will have to know the mean value theorem. You'll probably have to use it, but not in such a manner to where there's an interval for a derivative. That's nuts. But now you know, and no one's half the battle there, G.I. Joe. I will see you for the next exam. Bye-bye.
Don't forget to subscribe and ring that bell.